Welcome to this deep dive. And wow, you really outdid yourself with this one, listener. I
Oh,
mean, Ununennium, element 119. This stuff is seriously fascinating. All these articles, the research, I was hooked from the first page. I mean, it's
definitely.
an element that's like completely theoretical, right?
Yeah,
It's never even been seen.
right. Never been created, never
Exactly.
observed.
Yeah, just this like theoretical possibility for now.
For now,
So,
yes.
so okay, like for someone who's, maybe not a total chemistry whiz, can we just start with some basics?
Sure. Yeah.
Like, what is unennium? What makes it so special?
Well, it's element 119, right? Which
Yeah.
basically means it has 119 protons in its nucleus. And based on what we know about how the periodic table is structured, it should be an alkali metal.
Okay, alkali metals. So like lithium, sodium, potassium, those guys.
Exactly. Those are all alkali metals. And they're known for being very reactive, especially with water.
Right, like those videos you see online where they throw like a chunk of sodium in water and it just
Yeah.
explodes.
Exactly, yeah. Very reactive elements. And ununennium, if we ever manage to create it, is predicted to be even more reactive than its later siblings.
Oh, wow. Okay, now I'm intrigued. But if it's just another alkali metal, why is everyone so obsessed with it?
Well, it's not just any alkali metal. Scientists are predicting some pretty unusual properties for ununennium. For example, its melting point is predicted to be somewhere between 0 and 30 degrees Celsius,
Hold on, so it could be a liquid metal at room temperature.
potentially.
Yeah, that's crazy. Isn't that like super rare for metals?
It is. Most metals are solid at room temperature. But there are a few exceptions, like mercury, which you mentioned earlier. But ununennium could be the first liquid alkali metal.
Oh, wow. Okay, so we've got a potentially explosive liquid metal. That's pretty wild.
It is, and those are just a couple of the things that make ununennium so fascinating.
Okay, but hold on. You keep saying scientists are predicting these properties.
Yeah.
How can they possibly know what an element might be like if no one has ever seen it?
That's a great question. It all comes down to the power of patterns and the brilliance of the periodic table.
Oh,
Yeah, see, the periodic table isn't just a random arrangement of elements. It's organized in a way that reflects the recurring trends in their properties.
right, like how the elements in the same column or group tend to have similar chemical behaviors.
Exactly. So, by looking at how properties change as you move across or down the periodic table, scientists can make educated guesses or predictions about the properties of undiscovered elements.
So they're basically using those trends to extrapolate what ununennium might be like based on its neighbors and its family members on the periodic table.
Precisely. They look at the trends in the alkali metal group, for example, and use that information to estimate what might happen when you get to element 119. They also consider things like electron configuration, which tells us how the electrons are arranged around the atom's nucleus. And that gives us clues about how ununennium might interact with other elements.
Okay, that makes sense. So it's like a combination of detective work and educated guesswork, all based on the fundamental principles of chemistry.
That's a great way to put it.
But, one of the articles you sent mentioned something called relativistic effects. I have to admit, that one kind of went over my head.
Yeah, relativistic effects. Those
Yeah.
are super interesting. It turns out that when you get to these super heavy elements like ununennium, things start to get a little, well, relative.
Relative,
Yeah.
like Einstein's theory of relativity.
Exactly.
Whoa, hold on. You're telling me that Einstein's theory of relativity is involved in predicting the properties of an element?
Believe it or not, it is. The electrons in these super heavy atoms are moving so fast, close to the speed of light, that their behavior can't be explained by classical physics alone.
Okay, now that's just mind-blowing. So how does relativity come into play?
Well, one of the key principles of relativity is that the faster something moves, the more massive it becomes. And that applies to electrons too.
So the electrons in ununennium are like tiny little speed demons getting heavier as they zoom around the nucleus.
You got it. And that extra mass actually influences how they interact with the nucleus and with other atoms.
So it's not just chemistry at play here, it's physics too.
Absolutely. And that's one of the things that makes these super heavy elements so challenging and intriguing.
Okay, so to get a good picture of ununennium's properties, scientists have to consider not only the periodic trends, but also the mind-bending world of relativity.
Exactly. And to do that, they use incredibly complex computer simulations that take into account both quantum mechanics and relativity.
So it's like they're trying to write the biography of ununennium before it even exists.
That's a great way to put it. And while it's still theoretical, these predictions are incredibly valuable They can guide the scientists who are actually trying to create this element in a lab.
Speaking of which, I read that there have been a lot of attempts to synthesize ununennium. What's the latest on that front?
Well, so far, no one has managed to create it.
Oh, so it's still a theoretical element.
It is, yeah. But there have been some pretty impressive efforts.
So how do you even go about creating an element that doesn't exist naturally?
It's not easy, that's for sure. Scientists are using these massive machines called particle accelerators,
Yeah.
essentially these high-powered atomic cannons.
Oh, wow.
Yeah. They use these accelerators to smash lighter atoms together at incredibly high speeds.
And if they get lucky, those atoms fuse together and create a new element.
That's the hope. But it's a lot more complicated than just smashing any two atoms together.
I imagine so.
Yeah, you need very specific elements and very precise control over the collision energies to have even a chance of creating a new element.
What kind of elements are they using to try to make unennium?
One of the most common approaches involves bombarding a target made of berkelium-249 with a beam of titanium-50 ions.
Berkelium. Now that's an element you don't hear about every day.
It's not exactly a household name, is it?
No, not really. So what's so special about berkelium?
Well, it has 97 protons, and titanium-50 has 22. So if you add those together, you get 119.
Ah, the magic number for ununennium.
Exactly. But there's a catch. Berkelium-249 is incredibly rare and difficult to produce.
Just how rare are we talking about here?
Let's just say you can't exactly order it from Amazon. It has to be produced in specialized nuclear reactors, and it takes years to accumulate even tiny amounts.
Okay, so supply issues are definitely a major hurdle. What else makes creating unennium so challenging?
Well, even if you have your berkelium-249, the odds of actually fusing it with titanium to create ununennium are incredibly slim.
So even with all this advanced technology, it's still a long shot.
It is, yeah. It's a bit like trying to win the lottery, but the odds are even worse.
Oh, wow. Okay, so we've got rare materials and a tiny chance of success. Anything else working against them?
Oh, just one more little thing. Ununennium, if it is ever created, is predicted to be incredibly unstable, probably with a half-life of less than a millisecond.
A millisecond. So even if they managed to create it, it would basically disappear before they could even confirm it existed.
Pretty much, yeah. They would need incredibly sensitive detectors to even have a chance of catching those fleeting signals.
Wow, that's a whole other level of difficulty.
It is, but, that's part of what makes this whole field of research so exciting. It's really pushing the boundaries of what's possible in science.
I can see that. But I have to ask, if it's so difficult to create and lasts for such a short time, why even bother? Why are scientists so determined to synthesize unennium?
That's a great question. And I think it speaks to the deeper motivations behind scientific exploration.
Oh.
Yeah. It's not just about practical applications. It's about pushing the boundaries of our understanding of the universe.
So it's about testing the limits of the periodic table itself and seeing how far we can push the boundaries of chemistry.
Exactly. And there's another fascinating aspect to this whole quest for super heavy elements that we haven't even touched on yet.
Yeah.
The concept of the island of stability.
The island of stability. Now that does sound intriguing. I remember reading a little bit about that. What's that all about?
Well, it's this idea that somewhere out there, beyond the elements we currently know, there might be a region of stability where super heavy elements actually have much longer half-lives.
Wait, so we could potentially find elements heavier than anything we've ever seen, but they wouldn't just vanish in a blink of an eye.
That's the idea. And unennium, sitting right on the edge of the known periodic table, could be a key to finding that island.
Okay, now my mind is officially blown. So ununennium, this hypothetical element that's never been seen, could lead us to a whole new world of stable, super heavy elements.
It's definitely a possibility.
This is incredible.
It is.
We've gone from talking about a single element to pondering the very fabric of reality and the limits of matter itself.
That's the beauty of science, isn't it?
It is. Okay, I'm hooked.
Yeah.
Tell me more about this island of stability. What makes scientists think it might actually exist?
Well, it all has to do with something called magic numbers.
Magic numbers.
Oh.
What are those?
So you see, just like electrons occupy specific energy levels or shells around an atom's nucleus, protons and neutrons do the same thing inside the nucleus.
Ah, okay. So there's like a structure to the nucleus too.
Exactly. And just like electron shells, these nuclear shells can only hold a certain number of protons and neutrons. And when a shell is completely filled, we get what we call a magic number.
And these magic numbers, they correspond to particularly stable nuclei.
Exactly. Nuclei with magic numbers of protons or neutrons, or even better, both,
Oh, wow.
tend to be much more stable than their neighbors on the periodic table. It's like they've got this extra, like, nuclear glue holding them together.
Okay, so where does the island of stability fit into all of this?
Well, the island of stability is this hypothetical region on the periodic table where super heavy elements with a lot of protons and neutrons, might actually be relatively stable.
Stable, like not decaying almost instantly.
Exactly. And the idea is that these super stable, super heavy elements would have magic numbers of protons and neutrons that correspond to completely filled nuclear shells. It's like they've got this extra layer of nuclear armor, making them much more resistant to decay.
So they'd be like the superheroes of the periodic table.
Kinda, yeah.
They've got these special powers, these magic numbers that make them stronger and longer lived than the other super heavy elements.
Yeah. And some theoretical models even suggest that these super stable, super heavy elements might have half-lives of minutes, days, or even years.
Whoa, years. That's incredible. I mean, compared to like milliseconds.
Right.
That's an eternity. So wait, if this island of stability actually exists, could Ununennium be like a bridge? Like a stepping stone to reaching this island?
It's possible, yeah. You see, Ununennium, with its 119 protons, sits right on the edge of the known periodic table.
Right on the edge, yeah.
And it's close to some of the predicted magic numbers for these super stable, super heavy elements. So by studying Ununennium, even if we can only create it for a fraction of a second, we might gain valuable insights into the structure of the nucleus and the forces that govern nuclear stability.
So it's like Ununennium is a key that could unlock the secrets of this island of stability.
That's a great way to put it.
Okay, so we've got these magic numbers, this island of stability, these super heavy elements that might be more stable than we thought.
Mm-hmm.
Where do we go from here? What are some of the specific research efforts that are being made to try to create Ununennium and explore this whole new world of super heavy elements?
Well, as you mentioned earlier, several research teams around the world are on this quest, and they're using some pretty impressive technology.
Oh, yeah.
Yeah. The main tool in their arsenal is the particle accelerator.
The particle accelerator. Yeah, you mentioned that before. But remind me, how does that work again?
Well, it's basically a massive machine that uses electric and magnetic fields to accelerate charged particles to incredibly high speeds.
Like those atom smashers you hear about?
Exactly. And by smashing those particles into a target made of the element they want to fuse, they can sometimes create new, heavier elements.
Okay, so it's like a giant atomic billiards game.
Sort of, yeah.
Yeah.
But instead of billiard balls, they're using atoms.
And the stakes are a lot higher than just winning a game of pool.
Definitely. We're talking about creating entirely new elements that have never existed before.
That's incredible. So what kind of particle accelerators are they using for this kind of research?
Well, some of the most powerful ones are located in places like the GSI Helmholtz Center for Heavy Ion Research in Germany,
Okay.
and the Riken-Nishina Center for Accelerator-Based Science in Japan.
Those names sound familiar.
Yeah.
Haven't they been involved in discovering other super heavy elements?
They have, yeah.
They're kind of like the rock stars of the super heavy element world.
You could say that, yeah. They've got some of the most advanced facilities and expertise in the world.
Okay, so they've got these massive particle accelerators.
Mhm.
What else do they need to actually create and detect these fleeting new elements?
Well, one of the most important things is the target material. Remember how we talked about using berkelium-249 to try to create ununennium?
Yeah, they're super rare stuff.
Exactly. Well, they need to create a target out of that material, and that's not easy. It often involves, like, electroplating tiny amounts of the target material onto a thin foil.
So they're basically working with like microscopic amounts of this stuff.
Sometimes, yeah. It's incredibly delicate work.
And then they have to make sure that the beam of particles from the accelerator hits that tiny target just right.
Exactly. And even then, the odds of a successful fusion are incredibly low.
I'm starting to get a sense of just how challenging this whole process is.
It is, yeah. But then, even if they do manage to create a new element, they have to be able to detect it.
Right, because these super heavy elements are so unstable. They're not just looking for the element itself, you're looking for the telltale signs of its decay.
Exactly. And that's where some seriously impressive detectors come in.
Oh, yeah. What kind of detectors are we talking about?
Well, one of the most common types is called a gas-filled separator.
Gas-filled separator. How does that work?
So basically, when the beam of particles from the accelerator hits the target, a whole shower of different particles and nuclei is produced.
Oh, okay.
And the gas-filled separator uses a combination of electric and magnetic fields to sift through all those particles
Yeah.
and separate them based on their mass and charge.
So it's like a giant atomic filter.
That's a good way to think about it.
It filters out all the unwanted stuff
Yeah.
and leaves behind only the potentially interesting new elements.
Right. And then those selected particles are sent to a detector where they can be identified and their properties can be measured.
And all of this is happening incredibly fast, right? Because these super heavy elements decay so quickly.
Oh, yeah. We're talking about fractions of a second here.
So it's like a race against time to capture those fleeting signals before they vanish completely.
It is, and that's why they need these incredibly sensitive and sophisticated detectors that can capture those tiny flashes of energy and those fleeting particles that are released during these nuclear reactions.
So we've got the accelerators, the target materials, the detectors. It sounds like it takes a whole army of scientists and engineers just to pull off one of these experiments.
It does. It's a huge collaborative effort.
And I imagine the data analysis must be just as complex as the experimental setup itself.
No, it is, yeah. I mean, they're dealing with massive amounts of data, and they have to sift through all that data to find those rare events that might signal the creation of a new element.
So they're looking for a needle in a haystack.
More like a specific grain of sand on a giant beach.
Okay, so we've got this massive undertaking, these huge teams of scientists, these incredibly complex experiments. What are some of the major challenges that they face in trying to create and confirm the existence of these super heavy elements?
Well, one of the biggest challenges is simply the low probability of success.
Low probabilities, because what do you mean by that?
I mean, even with the most advanced technology and the most carefully designed experiments, the odds of actually fusing two nuclei together to create a super heavy element are incredibly slim.
It's like trying to win the lottery, but the odds are even worse.
Yeah, pretty much.
So they're really up against
They
it.
are, yeah.
Yeah.
And then on top of that, you have the challenge of actually detecting these new elements. I mean, remember, they're incredibly unstable, so they decay very quickly.
Right.
And that means that they have to have detectors that are sensitive enough to pick up those fleeting signals.
And not only that, they have to be able to interpret those signals correctly.
Exactly. They have to make sure that what they're seeing is actually evidence of a new element, not just some other, random nuclear reaction.
Right. So it's not just about creating the element. It's about proving that you've actually created it.
Exactly.
And that's where the real detective work comes in.
Yeah, it is.
They have to piece together the clues from those decay products, those particles and energy signatures, to build a case for the existence of this new element.
Precisely. And that can be really tricky, especially when you're dealing with elements that only exist for a fraction of a second.
Yeah, I can imagine. It's like trying to solve a puzzle where the pieces are constantly disappearing.
Exactly. It's a huge challenge.
But it's also incredibly exciting, right? I mean, the prospect of discovering these brand new elements, these new building blocks of matter.
Oh, it is. Yeah. I mean, it's really pushing the boundaries of what we know about the universe. And who knows, maybe someday we'll even find that island of stability.
That would be incredible. Okay, so we've talked about the challenges of creating and detecting these super heavy elements. What about the potential applications? I mean, what could we do with these new elements if we could actually create them in larger quantities?
Well, that's a great question. And to be honest, it's still a bit early to say for sure. I mean, we're still in the very early stages of exploring this realm of super heavy elements.
Right.
But, historically, new elements have often led to unexpected discoveries and new technologies.
Oh, yeah. Like what?
Well, I mean, think about plutonium, for example.
Okay.
I mean, that's a synthetic element. It doesn't exist naturally, and it has obviously had a huge impact on the world, both in terms of energy and weapons.
Right.
So it's hard to say exactly what applications these super heavy elements might have.
Right.
But it's definitely an area that's full of potential.
Okay. So it's more about the fundamental science right now.
It is, yeah. It's about expanding our knowledge of the universe and seeing how far we can push the boundaries of chemistry.
Right. It's about the thrill of discovery.
It is, yeah. And who knows, maybe down the road these super heavy elements will have practical applications that we can't even imagine right now.
It's mind-boggling to think about the possibilities.
It is. It really is.
Okay, so we've covered a lot of ground here. We've talked about ununennium, this hypothetical element that sits on the edge of the periodic table. We've talked about the island of stability, this theoretical region where super heavy elements might be more stable than we thought. We've talked about the incredible challenges of creating and detecting these super heavy elements. And we've even touched on the potential applications, although, as you said, it's still a bit early to say for sure what those might be.
Hmm.
So where do we go from here? What are the next steps in this quest for unennium and the exploration of this new frontier of the periodic table?
Well, I think the most important thing is to keep pushing the boundaries of what's possible.
Pushing, yeah.
To keep developing new technologies, to keep refining our experimental techniques, to keep collaborating with each other. I mean, this is truly a global effort.
It is, yeah.
And ultimately, I think it's about keeping that sense of wonder, that curiosity that drives us to explore the unknown.
I love that. The curiosity that drives us to explore the unknown.
Yeah.
Well said. Well, I want to thank you for taking us on this incredible journey into the world of ununennium and the quest for super heavy elements.
Yeah.
It's been an absolute pleasure.
It's been my pleasure too. I'm always happy to talk about this stuff. It's really fascinating.
And to our listener, thank you for joining us on this incredible deep dive.
Yeah.
We hope you found it as fascinating as we did.
We hope you learned something new.
And who knows, maybe you'll be the one to make the next big breakthrough in super heavy element research.
Until next time.
So, we've been talking about these super heavy elements, and you've mentioned that they have these really short half-lives,
Yeah.
which basically means that they decay really quickly.
Right.
And this makes them incredibly difficult to detect.
Yeah, absolutely.
So I'm really curious to hear more about how scientists actually go about trying to catch these fleeting elements.
Well, it's definitely a challenge.
Yeah.
But they've developed some really ingenious techniques over the years.
Okay, so what are some of the key methods that they use?
Well, one of the most important things is to have a really good detector.
Okay, detector.
A detector that's sensitive enough to pick up the very faint signals that are produced when these super heavy elements decay.
Right, because they're not lasting very long, so they're not giving off a lot of signal.
Exactly.
So what kind of detectors do they use?
Well, there are a few different types, but one of the most common ones is called a gas-filled separator.
A gas-filled separator. Okay, that sounds pretty high tech.
It is, yes.
So how does that work?
Well, basically, when the beam of particles from the accelerator hits the target, it creates a whole shower of different particles, right?
Right.
And the gas-filled separator uses a combination of electric and magnetic fields to kind of steer those particles
Okay.
and sort them based on their mass and charge.
So it's like a giant atomic sorting machine.
Yeah, kind of.
It's separating out the wheat from the chaff, so to speak.
Exactly.
And hopefully leaving behind some of those super heavy elements that they're looking for.
Right.
So the gas-filled separator does the sorting, but then how do they actually identify the elements?
Well, once they've separated out the particles of interest, they send them to another detector, which is usually some kind of semiconductor detector.
Okay.
And this detector can measure the energy of the particles that are hitting it. And based on the energy signature, they can identify what kind of particle it is.
Wow.
And therefore what element it came from.
So it's all about piecing together these little clues.
It is, yeah.
From the decay products to figure out what the original element was.
Exactly.
That's pretty amazing.
It is, yeah.
It's like atomic detective work.
It is.
Okay, so they've got these amazing detectors. They're able to separate out the particles. They're able to identify them. They're able to piece together these decay chains. What are some of the biggest challenges that they face in actually confirming the existence of these new elements?
Well, I mean, as we've talked about, one of the biggest challenges is just the sheer rarity of these events. I mean, you're talking about one atom in a billion,
Oh, wow.
So just finding that one atom is a huge challenge. And then, once you've found it, you have to be absolutely sure that it's what you think it is.
Right.
And that can be really tricky because there are a lot of other things that can happen in these experiments that can mimic the signal of a new element.
Okay. So there's a lot of potential for for false positives.
Serious, yeah.
So they have to be really careful. They have to really analyze the data very thoroughly.
Yeah, absolutely.
To make sure that they're not being fooled by something else.
Exactly.
And then, on top of that, you have the challenge of just the sheer complexity of the experiments themselves. I mean, these are massive multi-million-dollar facilities with teams of scientists and engineers from all over the world working together. And it's just a really, really complex undertaking.
It is, yeah. It's definitely not easy.
But clearly it's worth it.
Oh, yeah.
I mean, the potential rewards are just too great to ignore.
Absolutely.
I mean, we're talking about discovering new elements, new building blocks of matter, pushing the boundaries of the periodic table, exploring the fundamental nature of the universe.
Right.
And that's pretty inspiring stuff.
It is. It really is.
Well, I have to say, this whole deep dive has been absolutely fascinating.
Oh, good.
I've learned so much about Ununennium and the island of stability, and the incredible effort that goes into trying to create and detect these super heavy elements.
Well, it's been my pleasure to share it with you.
Well, thank you for being such a fantastic guide on this journey.
You're welcome.
And to our listener, thank you for joining us on this amazing adventure.
Yeah, thanks for listening.
We hope you've enjoyed it as much as we have.
And who knows, maybe someday you'll be the one making these amazing discoveries.
Until next time, keep exploring.